There is an underground structure built 2,400 years ago in the Persian desert that keeps food cold without electricity, without refrigerant, without any mechanical system of any kind. It uses the consistent temperature of the earth at depth. It uses wind towers above ground to circulate cool air through the interior. It uses the thermal mass of thick mud brick walls to buffer temperature changes. Multiple examples still stand across Iran. Some are still functional today. The interior temperature of a functioning yakshal, the Persian name for this structure, stays below freezing through summers, where surface temperatures reach 50 degrees Celsius. The $130 billion global refrigeration industry has not funded a single modern adaptation study of this technology. The structure that works without electricity is in the desert. The quarterly earnings reports are in the financial press. The industry knows where it prefers to direct attention. Not because the yaktil stopped working. Multiple standing examples prove it is still working. Not because the engineering is too complex to reproduce. A structure built from mud, brick, and wind by engineers working 2,400 years before modern materials science existed is not a complex engineering challenge by contemporary standards. Because a cooling system that costs nothing to run lasts centuries without replacement and requires no refrigerant, no compressor. And no power connection does not generate $130 billion per year. It generates nothing. That is the difference between a technology that is classified as an archaeological curiosity and one that occupies the kitchen of every household in the developed world. Subscribe and hit the bell. The next story opens soon. The archive opens in the city of Yazd in the center of the Iranian plateau. Summer temperature, 52 degrees Celsius on the surface. A desert so dry that rainfall averages less than 60 millimeters per year. A landscape where conventional food storage fails within hours, where unrefrigerated meat spoils before it can be transported to market, where vegetables harvested in the morning are inedible by evening. And in this landscape, 3,000 years ago, Persian engineers began building underground chambers that solved the problem completely. The yakchel, the name comes from the Persian words yak, meaning ice, and chal, meaning pit, the ice pit. The structure has two components. Below ground, a storage chamber typically between 5 and 20 meters deep, with walls of thick mud brick mixed with a compound called sarouj. Sarouj is a mixture of sand, clay, egg whites, goat hair, lime, and ash that creates a material more waterproof and thermally resistant than any natural brick. The chamber base is below the frost line where earth temperature remains between 10 and 15 degrees Celsius year-round, regardless of surface conditions. The thermal mass of the surrounding earth buffers any temperature fluctuation. Below ground, heat cannot reach the storage space. Above ground, one or more wind towers called badgers. The badger is a vertical shaft with openings oriented to catch the prevailing wind. Wind enters the openings, travels down the shaft, cools against the underground walls, and enters the storage chamber as cooled air. The cooled air is denser than warm air. It sinks. The warm air inside the chamber is displaced upward and exits through gaps at the top of the dome. The result is a continuous passive circulation of air that the underground earth cools on every pass through the shaft. No electricity drives this circulation. The wind drives it. The wind has been blowing over the Iranian plateau for longer than the human species has existed. The dome above ground is a second engineering feature, built from mud brick in a shape that distributes structural load evenly. The dome rises to heights of 10 to 18 meters, the thickness of the dome walls sometimes exceeding 2 meters. Creates thermal mass that absorbs heat during the day and releases it slowly through the night. The exterior surface is coated in the same sarouj compound that waterproofs the underground chamber. The dome maintains a temperature differential between its exterior surface and the interior air that assists the passive cooling cycle. On the north side of many yakshals, a long wall was built to shade the structure from direct sunlight during the hottest hours of the day. The combination of shade, thermal mass, earth temperature, and wind circulation produced interior temperatures that could reach below freezing in the coldest periods of the desert winter. Winter ice, harvested from nearby mountain streams or produced naturally in shallow pools during cold nights, was transported to the yakshal and packed into the underground chamber. Insulated by the earth above, cooled continuously by the wind circulation, the ice remained frozen through summer. The Kanat connection is important. Qanats are underground water channels that Persian engineers also developed, tunneling through mountains to bring groundwater to desert cities without pumps. The qanat delivered water, the yakchul stored ice. Together, they represented the most sophisticated water and temperature management infrastructure in the ancient world. Cities built on qanat and yakchul networks could sustain populations in desert locations that would have been uninhabitable without them. The ancient city of Yazd has been continuously inhabited for over 7,000 years. It sits in the center of one of the driest deserts in Asia. It survived because of water and cold storage infrastructure that required no energy beyond human labor to construct and zero energy to operate. The saruj compound used in yakdul construction deserves specific attention. Modern materials scientists who have analyzed historical saruj samples have found that the compound achieved waterproofing properties comparable to modern cement while being fully biodegradable and sourced entirely from local materials. The egg whites and goat hair in the mixture created a fibrous reinforcement structure similar to the synthetic fibers added to modern concrete to prevent cracking. Persian builders discovered fiber-reinforced waterproof mortar through empirical testing 2,000 years before polymer science existed. To explain why it worked, the mixture proportions they arrived at are documented in Persian architectural records and have been successfully reproduced by modern researchers. Persian cities of significance maintained multiple yakchuls. Archaeological evidence from the ancient city of Persepolis, the ceremonial capital of the Achaemenid Empire, documents ice storage facilities serving the royal court. The Achaemenid kings who built Persepolis in the 5th century BC served chilled food and drinks at court. This was not a luxury available only to emperors. Merchant families maintained private yakchuls. Communities built shared facilities. The infrastructure of cold storage was as ordinary in Persian city planning as the qanat, the underground water channel that supplied irrigation, or the bazaar that organized commerce. The engineering knowledge spread. Archaeological evidence of yakchul-type structures appears across the ancient Near East. The fundamental principles of using earth temperature and passive air circulation for cooling were applied in variations across the region. But the most sophisticated examples, the largest, the best preserved, and the most thoroughly documented, are concentrated in the Iranian plateau, where the combination of extreme desert heat and cold mountain winters made the technology not just useful, but essential. Now look at what replaced it, and when, and why the replacement happened when it did, rather than when a better technology became available. The first domestic mechanical refrigerators appeared in the early 20th century. General Electric launched its monitor-top refrigerator in 1927. It used sulfur dioxide as refrigerant, a toxic chemical that required replacement when it leaked, which it frequently did. Early refrigerators killed people. They killed enough people that refrigerant chemistry had to be reformulated. Freon replaced sulfur dioxide. Freon destroyed the ozone layer. International treaties required Freon to be replaced. The replacement chemicals, hydrofluorocarbons, are potent greenhouse gases. The refrigerant chemistry of the modern refrigerator has caused 3 distinct environmental crises since the product was introduced in 1927. The yakchel has caused none since it was introduced in 400 BC. The domestic refrigerator became the global standard, not because it was environmentally superior. It was not. Not because it was cheaper to operate over its lifetime. It is not. Not because it lasted longer. The average refrigerator lifespan is 15 years. A yakchul in Maybad, Iran, has been standing and functional for over 500 years. The domestic refrigerator became the global standard because it could be manufactured, sold, and replaced, because it required electricity to run, which was sold by utility companies, because it required refrigerant, which was manufactured by chemical companies, because it broke down and needed replacing, which generated repeat revenue. Whirlpool, annual revenue of $19 billion. LG Electronics Home Appliance Division, Samsung Refrigeration, Electrolux, Haier, the 6th largest refrigerator manufacturers collectively, generate revenues measured in tens of billions of dollars annually. Every household in the developed world replaces its refrigerator multiple times across a lifetime. Every replacement is a sale. Every month of electricity consumption is revenue for a utility company. The global cold chain, the refrigerated transportation and storage infrastructure that moves food from farm to table, is worth $250 billion. Every element of this system requires ongoing purchase of electricity, equipment, and maintenance. The Yakshul requires the wind to blow. The wind has never sent an invoice. In 1892, the British statesman George Nathaniel Curzon traveled through Persia and published a detailed account called Persia and the Persian Question. He documented Yakshuls in Yazd and other cities with admiration. He noted the consistency of their performance. He observed that Persian households maintained reliable cold storage through summers that would have defeated any contemporary European system. His book was published in London. It was read by engineers and colonial administrators. The electric refrigeration industry was developing simultaneously. The passive cooling chamber that required no ongoing purchase was classified as an interesting historical observation from a pre-modern civilization. The industry chose the version with the power cord. The specific year of transition is documentable. Between 1920 and 1940, electric refrigeration expanded from a commercial luxury to a household product across North America and Europe. In that same 20-year window, the last generation of builders who maintained traditional passive cooling knowledge in Middle Eastern and Central Asian construction retired. Their apprentices were trained in the new modernist construction methods that assumed mechanical cooling. The knowledge did not vanish in a single event. It diluted across one generation and was not replenished in the next. By 1950, passive cooling had been reclassified from standard practice to regional tradition to archaeological curiosity in the span of 2 decades. The refrigeration industry did not need to accelerate this process. Modernism accelerated it without any external pressure. No law prevented the adoption of Yakshul principles in modern construction. No patent blocked engineers from studying and adapting the technology. The refrigeration industry did not lobby against passive cooling research. It simply funded active cooling research. The difference between suppression and neglect is invisible in its effects. A technology that receives no research funding, no engineering attention, no curriculum space in architecture and engineering schools, and no industry promotion disappears from practical knowledge as completely as if it had been banned. The Yakshul disappeared from practical knowledge in the 20th century, not by force but by funding priority. The industry funded what generated revenue. The mud brick wind-cooled chamber generated none. There are architects and engineers working on this today. The field of passive cooling design draws explicitly on Yakshul principles. The thermal mass approach, the wind-driven air circulation, the earth temperature buffering are all documented in passive architecture literature. Buildings designed with these principles can reduce cooling energy consumption by 60 to 90% compared to conventionally air-conditioned structures. Several architectural firms in the Middle East and North Africa have built modern structures incorporating Badger-style wind towers with documented energy savings. The research exists. The results are published. The mainstream construction and cooling industry has not reorganized around the findings. The $130 billion refrigeration market and the $250 billion cold chain market collectively represent too large an economic interest to reorganize around a technology that reduces their revenue to zero. The engineers who know about passive cooling are not uninformed. The industry executives who read engineering literature are not ignorant. The economic case for maintaining the status quo is very clear and does not require any conspiracy to sustain itself. The most documented modern example of Yakshul principles applied to contemporary architecture is the downdraft evaporative tower designed by architect Nicholas Grimshaw for the Eden Project in Cornwall, England. The tower uses the same principle as the Badger wind tower. Air enters at the top, passes over water-saturated surfaces, cools through evaporation, and descends into the space below as cooled air. The system reduces air conditioning load in the building without compressors or refrigerant. Grimshaw did not invent this. He applied a principle that Persian engineers used in the 5th century BC. The architectural award his tower received did not mention the Persian precedent. The engineering literature that cites his work does not consistently trace the principle to its origin. The Zion National Park Visitor Center in Utah was designed with passive cooling features, including thermal mass walls and natural ventilation orientation. Studies documented a 60% reduction in cooling energy compared to conventional construction. Architecture schools teach the project as a case study in sustainable design. The Yakshul that demonstrated these principles 2,400 years earlier is taught in archaeology courses, not architecture courses. The principle crossed departments somewhere in the 20th century and lost its engineering context in the transition. Here is what you can take from this. The engineering principles of the Yakchal are applicable at small scale. The Earth temperature principle works in any climate where the ground below frostline maintains a stable temperature. In most of North America and Europe, this means a basement or underground root cellar maintains temperatures between 10 and 15 degrees Celsius year-round without any refrigeration. A well-built root cellar with good insulation and ventilation keeps vegetables, dairy, and preserved foods for months without electricity. This is not the same as a yak. It does not achieve below freezing temperatures, but it operates on the same principle, and it operates for free. For households in hot climates, the thermal mass and wind circulation principles can meaningfully reduce air conditioning load. Thick walls absorb heat during the day and release it at night when outside temperatures drop. Oriented ventilation openings catch prevailing breezes and move air through the structure. Strategic shading prevents direct solar gain on walls and windows. None of these features require electricity. All of them reduce the electricity that air conditioning requires. The passive cooling research community has documented these effects across hundreds of case studies. The results are consistent. The adoption rate outside specialist architecture remains low. The Yakchal in Mabad, Iran, was built in the 15th century. It is approximately 17 meters tall above ground. Its underground chamber is 12 meters deep. Its mud brick dome stands intact. The sarouj coating on its exterior has weathered 500 Iranian winters and summers without structural failure. The wind towers still stand. The fundamental engineering of the structure is unchanged from what Persian engineers developed 2,400 years ago. Your refrigerator was manufactured in the last 15 years. It will need replacing in the next 15. The electricity it consumes this month will be billed next month. The refrigerant inside it will eventually leak and require certified technician recovery to prevent atmospheric release. When the compressor fails, repair will cost more than replacement. You will buy another refrigerator, the cycle continues. In the desert, the wind blows through a mud brick tower into an underground chamber and keeps it cold. It has been doing this since before Julius Caesar was born. It has not sent an invoice once. The 15-year lifespan of your current refrigerator is an engineering choice, not an engineering necessity. A refrigerator built to last 50 years would cost more to manufacture and would generate revenue once instead of 3 times across the same period. The industry calls the 15-year cycle a product life cycle. The Yakchal in Mabad calls it 500 years of uninterrupted service from mud and prevailing wind. The difference between those two sentences is not technology. It is the difference between what a market rewards and what physics makes possible when nobody is trying to sell you the next unit. The Persian engineers who built the first Yakchal had a desert and a problem. The solution they arrived at is still standing, still cold inside. Subscribe to and hit the bell. The next story opens soon.